In this video, I want to show if certain vectors are linearly independent. So for example, suppose that we have three vectors, v1, 1, 1, 1, v2 equal 1, 2, 3, and v3 equals -1, 1, -2. And let's try to answer this question. Are v1, v2, and v3 linearly independent? Remember that linearly independent means that they cannot be written as a linear combination. A very similar question would be to ask if they are linearly dependent. So we can say that vectors are linearly dependent if we have, for example, that A v1 plus B v2 plus C v3 equals 0 for A different from 0, B different from 0, and C different from 0. If we have numbers different from 0 that make this vector equation to be true, we call this linearly dependent. Another way, another equivalent way that we can think about this is, for example, if we can say that v3 is part of the span of v1 and v2. That's an equivalent way of saying that vectors are linearly dependent. Now, linearly independent means that this is false. Linearly independent means that, for example, we can say that the span of these three vectors, it's actually all of R3. So there are equivalent ways that we can think about this. And let me try to actually focus on this way. In other words, what I'll do for this problem is that I'll evaluate if this equation has non-zero solutions. In other words, if there are non-zero solutions, we have that this will imply that the vectors are linearly dependent. But on the other hand, if we have that A, B, and C are actually equal to 0, that means that they're linearly independent. This is a very simple way to check if a set of vectors is linearly dependent or independent. So all I'm going to do is I'm going to look at this equation. Let me write down the vector equation. 1, 1, 1 plus B, 1, 2, 3 plus C, -1, 1, -2 equals 0. And I'm going to write down the matrix related to this system. So this will be 1, 1, 1, 1, 2, 3, -1, 1, -2. Notice that on purpose, I'm going to left out the 0 that I have over here. I could write down the augmented matrix for this, but I'm just going to focus on the coefficient matrix. I'm just going to focus on that coefficient matrix since I already know that the last row of the augmented matrix is going to be 0. The last row for this augmented matrix will be 0. And the reason for this is because we're talking about a homogeneous system. So I'm going to focus only on the coefficient matrix, and what I will do is I'll just reduce to echelon form. So let me work out this one over here. I can actually start getting rid of these numbers. So I'll just replace the second row by the second row minus the first row, and I'll replace the third row by the third row minus the first row. And if I do these two operations, the first row will remain the same, 1, 1, -1. The second row will be 0, 1, 2, and the last row will be 0, 2, -1. So I just did those two operations at once. Now notice that I can also replace the third row, if I want to keep doing this, I can replace the third row minus 2 times the second row, and that will get rid of this number right here. So if I do that, the first two rows will remain the same, and then my last row will be 0, and then that will give me -4, I believe. So this is good. Now in order to finish my echelon form, I'll replace the third row by -1/4 of the third row. That will make this to become a 1. Remember that whenever we have matrices, we need our echelon forms to have 1s for the pivot positions. So now we have an echelon form. And now with this, I'm actually not going to do the reduced echelon form because in this case, it is not necessary to do that. If I look in here, if I write down this into my system of equations, then I will end up with the following system. Remember that this is a homogeneous system. So that means that the last row is always going to be an invisible row of zeros. Whenever we have a homogeneous system, we will have that augmented matrix is always going to be a column of zeros. So with this, we have that C equals 0. And if C equals 0, I can plug this back into the second row and I'll get the B equals 0. And if both of these are 0, then from the first row, I get that A equals 0. In other words, if I look at my original vector equation, if I look at this original vector equation up here, the only solution that I have for this vector equation is for all three scalars to be equal to 0. And that is exactly what I have over here. If all three scalars are equal to 0, if that is the only solution, that means that the three vectors are linearly independent. In other words, I can phrase this in a couple different ways. I can say that V1, V2, and V3 are linearly independent. I can also say that V3, for example, is not in the span of V1 and V2. That's equivalent. And then another way that I want to write this down is that the span of V1, V2, and V3 is actually all of R3. Any of those answers are equivalent. We have that all those three answers are equivalent to each other. That means that they really mean the same thing. And really what we had to do was just to solve that original vector equation.